probably like 10 minutes early so I can hand those back. I just don't want people looking at stuff while we're doing other things. Are there questions over the homework at this point? Yeah.
For 8.2, the reduction formulas, are you going to give us that a specific formula to go by on the exam?
Oh, yeah. So yeah, the reduction formulas in 8.2. No, I won't give you those. I'll give you ones where you don't need those.
I got you. Yeah, because they gave us like 4 different examples.
Yeah.
Yeah, I just didn't use them.
Yeah, you can get by a lot of them without using them. We'll see in like the next section too. There's also reduction formulas for like powers of trig functions, and depending on the situation, sort of the way around it is to use reduction formulas. So we don't really do a whole lot of those examples either, just because the ones we do we can use by integrating by parts or by other methods. And I don't want to really take away from that by having you remember other formulas that you don't necessarily need. So yeah. Yeah. 8.1, number 6. Yeah. Start over. So evaluate the following integral. Yeah, let me just put that in my notes. Number 6. All right. So, any ideas on how to handle that? So yeah, in a form of 1, what would be? Okay. So what are you saying, like we should take this and multiply it by something that'll get rid of the radical in the bottom? Okay. So what would that be?
X squared, right?
So if we multiplied x squared, we would have x squared minus x squared times x to the 1/2, or x to the, 5/2. Just to have that like funky radical or that power of x. 1 plus root x, yeah, the conjugate. I don't know if this will work or not, but we're certainly going to try it. Okay, so that gives us, I have a mess on the top at this point. What do we have on bottom?
This is just 1 plus x.
1
minus x.
Yeah, 1 minus x. This is a minus b. This is a plus b. The product is a squared minus b squared. A squared minus b squared. So I don't know, that doesn't look much better, right? In terms of like integrating it, we have a 9 minus 9x minus 9 root x on top. Minus 9x root x. So although it's true that we just have powers of x on the top, we still have that denominator to contend with. So I mean, maybe at that point we could break each one up over the 1 minus x, but I don't know if that's going to help either, so. And we can certainly find the antiderivative of 9 over 1 minus x. This one might be a little more difficult than this one. Maybe even more difficult. I'm not sure.
Did you factor out the 9 before you put the top?
Yeah, we could take the 9 out as a constant. That's really not the issue. This one here is basically in log form, the first term. The second one, not looking good.
Aren't we missing the last term, 9 root x?
9 root x? Where do you mean the last term?
As in when we FOIL it out.
Oh, yeah, we miss, I forgot. I see that causes me to mess up. So yeah, we do have an additional term, my bad. But either way, not looking good, right? So what do we miss? 9 minus 9 root x. We have minus 9x. 9 root x. 9 root x. Squeeze that in there. 9 root x over 1 minus x. Okay, yeah, so it doesn't look great for integrating that. So I don't know. I would probably stop there. I mean, we could attempt to integrate each one, but it certainly seems like that's not lending itself to an easier process, right? Okay, so other ideas for this? Well, yeah, we wouldn't be able to do long division.
Well, before you FOIL it, can't you just take the 9 out of the first set? You get 1 minus x times 9?
Yeah, so I think that's the better way to look at it. So I think if we looked at the integrand as 9 times 1 minus x all over 1 minus root x, then that'll be a little more helpful. So it still doesn't look like we can cancel anything, right? And I think we're not really accustomed to looking at 1 minus x as a difference of squares. I mean, sure, 1 is a square, but when we see x by itself, we don't really think of that as a square, right? But couldn't we say that 1 minus x is 1 minus root x times 1 plus root x? Isn't that kind of what we did when we used the conjugate? So that's, if we factor 1 minus x into 1 minus root x, 1 plus root x, then we have that thing canceling out, and we just have 9 times 1 plus root x. Or 9 plus 9x to the 1/2. Which then, of course, we can integrate that. I mean, you can leave the 9 out too if you want, whatever. But the point is, we've simplified that function to this function, which we can find the antiderivative of. So it's more of a subtle factoring technique that's utilized here. I'm sure you can complete that pretty easily. And usually you don't factor stuff like that. The only reason we factored it like that is because of the 1 minus root x on bottom. So. Anybody have any questions about that? Again, it's not always a straightforward process like, oh, hey, this looks like something I should try. It's not always guaranteed that that's going to work. All right, any other homework questions? So then we left off in 8.2, integration by parts. The last one we looked at is the integral of ln x with respect to x. Being x ln x minus x, you know, I think that's a common enough function that you should just remember that integral. Whether you want to remember the whole process of integrating it by parts, or if you just want to remember that it's x ln x minus x, either way, I think you should definitely remember that one. All right. So did anyone have any questions on the integral for the natural log? No. Okay. Here's another type of instance that we run into when we integrate by parts. So e to the x cosine x. We'll do this. We'll look at this integration by parts, official way, I guess, and then we'll look at it with tabular integration to show, you know, that you've got to still recognize at some point, if you're using that tabular integration, when to stop in some instances. So what should our u and our dv be? U would be cosine x. And then our dv then is the rest of that, e to the x dx. So we have du as the derivative of u with respect to x. Sorry, derivative of cosine. And then the integral, the antiderivative rather, of dv. So let's write it out here. Our original integral of e to the x cosine x dx is u times v. E to the x cosine x minus the integral of v du. So I just recommend putting things in as they are, and then you can reconcile the signs after you've put things in. Just try not to get ahead of yourself and say, oh, that negative is going to make a positive and put that in, unless you're like super confident or you've been getting these right. Because I think one of the biggest issues when we integrate by parts are those signs, especially the sign on the negative of this integral that people tend to mess up on. Okay, so we put that in, minus the integral and minus e to the x. We'll just call that a positive now at this point. And then we said that the integral of v du here should be comparable or easier than what we had. It certainly looks comparable. I don't know that it's easier. So then we'll do this again. So u is sine and dv, once again, excuse me, e to the x dx. So du cosine x dx and v e to the x. I think this is always the important phase in which you do integration by parts more than once. Maybe not necessarily here because we don't have the minus integral, but a lot of times you have that minus integral of v du. And when you split this the second integral up again into two different pieces, uv minus the integral of v du again, just be careful with those signs. You know? So like if it's, you know, I don't know, uv minus the integral of v du, if that integral then is a second time with integration by parts, you're going to break that up into another uv minus the integral of v du. But both of those pieces have that original negative in front of it, right? So just be careful with that. So here we have the integral of our original. So all of this, the second integral turns into u times v minus the integral of v du. So then we see the issue, hopefully, with this process, right? Now we're back to what we started with this integral of e to the x cosine x. With these types of problems, it's crucial that you recognize we've got to stop here because we've already seen what happens when we integrate this by parts. We break it down 2 more times, we're back to where we started again. We're just adding more and more terms, still never resolving what the actual integral or the antiderivative was. So when you recognize that, you've just got to solve for this integral. I've got this minus e to the x cosine x integral over here, and I'm just going to add that to both sides, like an algebraic equation I'm solving for. And so I have now 2 of these on the left-hand side. Equaling e to the x cosine x plus e to the x sine x. Yeah, does that make sense? Any of these ones, like where you just keep getting the same integral after a couple of repetitions, you always end up solving for that integral. So to solve for the integral, we're just going to divide through by 2. So the antiderivative is all of that stuff over 2. And we have some constant. And so oftentimes you see this written with a 1/2 and the e to the x out, and just cosine plus sine. I would say that's typically how you see that, but either one's fine. So sometimes we do end up with these, a little bit more of a unique situation where we do just have to algebraically solve for the antiderivative. And those, like in this example, those come out when you end up with the same integral that you started with. Just like we did here in this second step of integration by parts when we ended up with that. Do y'all have any questions on this example? So once again, if you're a fan of tabular integration, we still choose our u as cosine, and our dv was e to the x dx. And remember the u's we just take derivatives of, so we have, we'll just write these out. Minus sine, minus cosine, sine, cosine, and on we would go remember the derivatives here, or the antiderivatives, the second one needs to be a negative, positive, negative, so to alternate these signs. Positive, negative of that, positive, negative of that, positive, whatever, right? It's a crucial step if you're using tabular integration. And then the antiderivatives on the right-hand side. That would continue as well. So at some point you have to know when to stop, right? Because this doesn't yield anything that terminates like the other ones we've looked at. Still the same idea though. Cross here. When we cross, we just multiply with the functions. So that's going to be e to the x cosine x. Cross again, we have negative, negative sign. So we have sine x e to the x. Oops. But then we wouldn't want to say again that we've got a negative cosine e to the x. It's at this point you have to recognize that the original integral involved e to the x and cosine. So when I move horizontally, I still take their product, but I put the integral in front of it. So their product is negative e to the x cosine, but since I've moved horizontally, I have the integral of that. So you'll recognize that hopefully as the same place we ended up with before we solved for the integral. So I don't know which method you prefer. Personally, I don't care what you use because tabular integration is integration by parts. It's almost like equivalent to synthetic division when we're dividing polynomials. So anyone have any questions on that? Excuse me. Okay, so it says verify the following reduction formula. I'll just remind you, there's no need to know this. Because you'll notice, even if you use it, like if the powers are high enough, you'll eventually kill off that integral, but you're still having to integrate something, whether you're integrating this by parts or you're utilizing the reduction formula again, and then again, and then again. But how this comes about is we've got a algebraic function with x to the n and an exponential function. So we would say our u is going to be x to the n, and our dv is e to the x dx. We have our v is e to the x, and du is n times x to the n minus 1 dx. So with that application of integration by parts, the reduction formula follows. So u times v minus the integral of v du. And since that n is a constant, they just pull it out. So it's the only difference. So, for instance, if this were like x to the 5th e to the x, then we would have x to the 4th e to the x x to the 5th e to the x minus the integral of x to the 4th. Then you would have to use the reduction formula on that integral again to get another uv integral of v du. Use it again and again and again. So there's no need to know that. All of the ones that would show up on the exam, you wouldn't need that reduction formula. So something like x cubed e to the x, I don't even think the reduction formula, even if you knew that, is the most efficient way to tackle that. This is going to be integration by parts 3 different times. So in my opinion, tabular integration is the most efficient way to do this. So let's just look at that. If you want to do this, just straight up integration by parts, then please attempt that. That way you can, if you want, you can practice, are all of my signs correct? Do I have all the right terms? So are U algebraic function and its derivatives? No more derivatives after that, so we stop. And we remember to alternate these signs. Positive, negative, positive, negative. Our dv was e to the x. So remember on the right, this right column, it's antiderivatives. We don't really see that with e to the x. But it is antiderivatives. So then we'll cross. That's x cubed e to the x. Then we've got a cross again, minus 3x squared e to the x. Plus 6x e to the x. Minus 6 e to the x. There's nothing else to cross, so with that one we know we're done there. Just add our constants. That's it. Like I said, if you've got extra time to go through this one with just the standard integration by parts approach, that's probably a good thing to do because you're going to do that 3 different times. Make sure you have all the correct terms and the correct signs in there. Is that tabular integration making sense to y'all? Is that okay? All right. So like I said, if you want to use that on the exam, I don't care. Any questions on this? Okay. So then we can talk about integration by parts for definite integrals. So when we do this, when we say it's u times v, we've already found a portion of that antiderivative. So we have the antiderivative here, uv, evaluated from a to b. But then we still have to find the antiderivative of v du. So honestly, what I would recommend is the u's and the v's and the v's and the du's, whatever you end up with, they all share the same bound, right? It goes from a to b. So I would just find the complete full antiderivative first, and then just evaluate all of it from a to b. Instead of trying to keep up with 2 different sets that have the same bounds, I think it's easier just to do the antiderivative first. Okay. So for instance, we would say u is x and dv is e to the 9x. Du is dx. And v would be what?
1/9 e.
Okay, yeah, right. Antiderivative, so 1/9 e to the 9x. Sorry, dv has the dx with it. there isn't anything wrong with how they've kind of broken this up above in the formula. If you want to keep track of things that way, feel free to do that. I just personally find it easier to do it all at the end. All right, so yeah, integral from 0 to 2, x e to the 9x dx is u times v minus the integral of v du. So then, to be a little more technical, let's take off the bounds initially. So we're just finding the antiderivative. Okay. And what's the antiderivative of 1/9 e to the 9x? One over, yeah, 81 e to the 9x. So now that we're done with the antiderivatives that show up, we can then just evaluate this from 0 to 2. Yeah. All right. Okay, so 2 in first. We have 2/9 e to the 18 minus 1 over 81 e to the 18 for f of b. We subtract off f of a. This first term is 0, and we have minus 1 over 81 e to the 0, which is 1. Is everybody all right with that? Find the antiderivative, then plug in the balance. So what do we have? 18 over 81 minus 1 over 81. So you have 17 over 81 of those. And then we have our 1 over 81. So as far as like interpreting that integral, there's not any pi's involved, right? So we know like it's not one of those volume formulas. So, maybe the best we can say is the curve x e to the 9x to the x-axis from 0 to 2, that's the area under that curve. Any questions on that? All right. So here's a harder one. I want y'all to try this one. There's a few things to pay attention to. If you don't like z's, that's fine. I don't care for z's either. So x inverse secant of x dx, that's fine to work with. It's the same thing. So also just a reminder of the acronym, how we choose our U. And that's, by and large, that acronym is useful. In the next section, we'll see an example where it kind of falls apart, but by and large, we use that here especially.
That just goes down.
you don't remember stuff about the inverse secant, look it up. I think even just you looking it up on your own is probably going to give you more of a, oh yeah, than me telling you what it is.
Is it arc secant?
Yeah, arc secant or inverse secant, either one.
No, that's arc.
Yeah, so. Yeah, they're missing a division.
Yeah, it's 1 over.
Yeah.
I was like, this doesn't seem right.
That is not useful, so I can't derive that.
Just also a hint as well, once you figure out the stuff for arc secant, just keep in mind the bounds of the integral as to give us some bearings on what x is, can help you get rid of a nuisance that's involved. Sure.
Really cute.
Oh, yeah, when Meredith gets
Actually,
ran over by his car.
Yeah, but then you're going to integrate that. Why don't you just do it like this? But I don't want to integrate. This is the thing.
No, so, it's just,
I'm assuming you changed the first. Yeah.
I thought it was like 1 over the square root.
no.
Yeah.
What was supposed to know? Okay, so what you do is that you integrate by parts. U is arc secant, and Z is dv's x.
That's what I wrote in my notes, like on that page. See, I think that's why I was curious. And that's also why I'm asking.
This is this, and
Yeah, that's what
it's this.
Yeah, that's what I was getting
No,
at.
just that becomes like
1 over x squared. Yeah, see, I'm like, can't be.
that's the one.
First part makes sense, Gary.
Yeah, I can remember. So U equal to arc secant.
He said if you look at the bounds, you can like skip the hard part, which I'm guessing is the square root. Like you skip the square root. What's the bound?
Almost be how.
What's that?
Wait, the square root
I feel like
is
I
2 squared.
I was getting pretty close to you.
I think they were trying to go that negative.
Okay, wait.
I can't wait to show you.
To show that it's.
dv is equal to x.
Yeah, I got it. Did you get
That's how you do all this stuff.
Du is not the log of 1 over x plus square root of x minus 1. X minus 1, right?
Now this is a good thing.
Yeah.
U is arcsecant.
Actual name.
Why are you
Oh, that's it.
Almost some
He's writing.
my attitude application. Just online.
He's writing that the river bed is equal to what I wrote. Yeah. So I got that.
And I love it. Like, you have to have like a year by them.
Nice.
Yeah.
Oh.
Almost done. I'll submit it tonight.
Yeah, guys, you don't need the answer.
I'll send it to you.
Dude, my online physics class is flatter as hell. Yeah. Which is that. Yeah. On my online physics, the final is worth 10 points in a quiz. It just isn't a final. It's just like on the test.
How'd you do in the test?
If I look, I'm just gonna want to see what I did wrong. So I just wait until I see it in person.
I would have done well. I literally had the biggest algebra brain fart of my whole existence.
Wait,
It's like everything is algebra, so like, okay, I don't
Yeah. Wait, what are two?
you changed your
You got x over 2 times squared.
Yeah, I think we might have done it.
x squared over 2 times 1 over x.
to what I had originally written down and scribbled out. I'm pissed.
Yeah.
Yeah, because I did it like that. I just, that way it's easier.
I don't even know.
It's much easier to choose.
How did I get here?
Squared
How did I
times
end
1
up here?
just use something, right?
Because the one.
X squared minus 1 and then
Maybe I should have
2x.
Probably pull a 1/2 out to make it easier.
Yeah. Pull the 1/2 out. And then you're gonna have to pull out another 1/2.
So that would be it? This is
No.
algebra.
You wanna pull out a 1/2?
Oh, it's inverse.
Erase
So you're gonna
it.
divide it so out.
Inverses are before that.
It's all right.
I'm going with artsy. Oh,
DU.
yeah.
Arcsecant is the farthest to the left.
Also, you
Arcsecant
don't
is
want
over here.
to.
That's why I had it on the side originally.
So secant inverse is u, d is that, right?
Yeah. No. Wait.
And then that'll help.
So that means.
Yeah, so the inverse secant is
Well,
not,
I did.
It's not the same thing as, secant to the negative
So
one.
then you plug that.
Secant to the negative
And
one
then it
is
becomes
1/4.
1/4 of what you said.
But inverse secant is completely different.
Because you're gonna plug that into the x.
Yeah.
Work law.
Can you pull that out right away?
Yeah. So you get a 1/4.
Another way for that.
Integral of, and it's just gonna be 1 dv square root of u, right? Which means to negative 1/2, which becomes
Which means it's
u to the
negative
1/2.
1/2. But you add 1, you get u to the 1/2 divided by 1/2.
No, 2 u to the 1/2. Is if you apply
Yeah,
1/2.
yeah, that's what I was saying.
Yeah, because you have to apply 1/2. So it becomes, yeah, u to the
So
1/2.
1 over the absolute value.
And then u would
No.
Yeah.
The square root of
By the
the square
Because
times
it's
1.
4, 2.
Well, yeah, you're gonna, yeah. Well, are you gonna put it back in?
Oh,
It is.
No, I know.
You could, but why?
I'm not gonna measure this. Now you got this, and then you
Well,
apply
we are
it.
now, right?
It becomes
Because we made it
x
useful.
squared equals to r
so that should have like, they
Yeah, no, I was thinking the same thing.
instead of
minus
saying like inverse secant, you have the absolute value of x.
That's what I was thinking.
This changes place.
Wait, yes, I did. We did it.
Oh, wait,
But they were valued.
Okay, so,
Yeah. And so that's when the bounds on x can come in.
So
For that absolute
it's gonna
value.
be 2 to the
Okay.
1/2.
Wait, is this the last example?
Yeah.
And I'm not gonna write
It's not even
that.
horrible. Make this into x. It's not even
You just, it's exams right now, right? You don't have to.
Yeah.
I don't know if the secant or secant too.
Yeah, you can get an exact value for that.
Wait.
Oh, this is also that way. This is also evaluated. That's really annoying.
Yeah, the whole thing is evaluated. That's why I just.
Well, the twos will cancel as well.
Yeah, you can take off 1/2 now. I'm glad I have 1/2 parentheses x squared r squared arcsecant x minus 1. The square root of x squared minus 1. And what are the two values? Square root of 2. Yeah. 2 and okay. So it's 1/2 4 arcsecant 2 minus the square root of 3 minus 1/2.
No, yeah, you are. Putting it at you. Telepathy.
4/3
Then you find it. Yeah. Derivative. Value. Alright, and then dv is z dv.
Where is it? Yeah. Exactly.
The derivative and
I got.
I'm pretty fast at mine.
process. Yeah.
I don't know. Look at this. Not simplifying this. I'm sure I could.
Oh my god. Apparently becomes 5 pi minus 3 squared root of 3 over
Oh, the
9.
integral, that is literally, yeah, that's actually.
I have no functions like that.
Well, 2 divided by square root of 3 secant, you could probably find that probably multiply. I can't imagine the secant inverse of 2 is something similar.
Yeah. Apparently it is though.
I don't know, so I did that part wrong. But I feel like we got to this
No, I
part,
feel
right?
like this is definitely correct. Okay, wait. This is correct. This is correct, but you can simplify this. Is what I feel. This is just correct.
But I think that was
If you're gonna do
yeah.
I guess you could say that.
It's just, we're trying to figure out these things on there.
if this was a test, this is where I would do that. I'd be like, oops.
Oh wait, we can literally just do another integration, right? Because this one.
Yeah, it's in pieces, but I know that like, this has to
Yeah, I'm pretty sure.
Yeah.
Where we were. Yeah. So we got it before we plugged it in correct. And then we plugged it in and haven't simplified it.
The online version has much simpler.
Yeah, the online, it says it becomes 5 pi minus 3 squared root of 3 over 9.
Yeah, that's right.
So how do you get from
And then you
this
get
to
by
this?
Is this, are we right up to this point?
Yeah.
This is right?
Yeah.
Oh, I never changed the U.
No, we still have to back in X.
I didn't.
Oh, well, I did.
I needed to. Okay, that's
You
what's
want to swap X back in.
Minus 1.
But I still
Well, no,
get
no, we
this.
get this.
Yeah,
We get this
so
integration.
once everybody kind of gets in the same spot, we'll talk about.
Oh, no, wait,
It's like,
this makes
if
it.
secant 2, how does that become a thing?
Well, yeah, that's the problem. I don't think a lot of calculators have even have an inverse secant button.
I know this.
Yeah, we'll talk about.
I don't know what to do at all from here.
Yeah, so this absolutely works because the bounds on X are
Not
positive.
even kind of like
Okay.
So like we don't need to have that there. It was X is range, if you will, and it's positive.
Okay,
That's
so that's.
two.
I haven't used my like $200 calculator since I was
Here you go.
anything you
Oh.
I don't know if that's true or not, but for here,
Yeah, that's.
here, I'm
Make it
not
an
allowed
X.
to use it in physics, I'm
And then
not
you
allowed
can
to use it in
submit
physics
it.
class, I'm not allowed to use it in my chemistry class.
Dude, my physics,
Oh, yeah.
I have like 9 different constants and I can't. It's like, what's the electrode?
So basically.
I have like,
Nice thing about those online classes is I have there's a chemistry
It's like, okay, I'm doing it, I'm just like, what the fuck? It's like, what doesn't create an electronic charge? I'm just like, we'll find out.
I should have taken physics.
Online classes usually there's a lot more player where you can get a better grade easier, but it's a lot more. And it's like there's a lot more confusion because you just trying to not do the question.
Oh, yeah. I'm just, yeah, I just get somewhere, I'm just like, I can't do this homework problem, no matter how hard
But I didn't
I'm
want to take physics online, so I was like, damn, I might be able to get a better grade by putting in so many hours, which I don't want to do. But I put so many hours into the in-person class too. We have class 3 times a week for 2 hours. They go to fucking tuition for like 2 hours a week. It's like usually have homework time to do.
Oh, you are too.
It's a couple hours. It's not easy. It's top of the way. Every class is reading.
Has 2 homeworks due a week, and when you want to spend 10 hours on each homework assignment, and we don't cheat on it, it literally takes that long.
Yeah.
There are like 70 questions from the book, you can write it all.
Yeah, no kidding.
I definitely spend more time on physics than I do on other classes.
I have 2 homework assignments due tomorrow, but I haven't started.
Wait, but it's 10 hours?
Yeah.
Yeah,
Yeah, but I'm gonna cheat on it. I
was like, I don't think there's enough hours.
I started paying for Chegg study, so that I could just get all the crap over.
It's fire.
I know, it's so fire.
Amazing, good solutions, like detailed solutions.
But then sometimes I'm like, where do you get these equations from? Like, these formulas.
Oh,
They're not even in the
Just
book.
whip out equations.
They're not even in the book.
Super specific.
I'll read the whole chapter, and then I'll be like, I have no idea how to figure this out, and then I'll go and check, and they're like, duh, you use this equation, and this formula, and I'm like,
Yeah, so I looked at all the challenge problems, and then on my like sheet for the test, I put down all the like formulas that they just like pulled up. And that worked out perfectly for one of the questions. I like the hard question, like the shooting the thing up to the hill question. I just used my tangent formula. I didn't do anything. I just instantly had the right answer, and I like moved on.
dude, my test was rough. I don't think I actually got a single question right. I just got a whole lot of partial credit.
I ended up with like a 91 after like a 10%. I should have done better. I just completed this first time on the service.
So do
I was like, I'm gonna bring it. So you guys can go. I'm kind of jealous that I wish I took your class. I wish I took this class.
No, that's not what it's for. That's a completely side thing. That's like not worth any in class anymore.
Oh, that's like I was gonna just come out.
No, he's gonna do it.
I think that's so. I think that's too.
No, I thought he said the catapult was only like, that's just like a side thing you can do if you want to like be a thing.
But like, if not, you want to be on a team? Can you be on a team with someone from a different campus? This kid that's, it's just like me and him.
I don't think you can because like you're trying to like, we're fighting their campus for the trophy.
He does, yeah.
Okay, yeah, I was like, taking a minute, I was like,
And I know we got like.
not crazy, but yeah, that makes sense.
Dude, I got invited to a group, like,
Oh yeah, he's on top of
my
the.
lab partners are partnered with the person who won it last year. We can just reuse the same catapult, and apparently it was amazing. And they asked me to be on their team, and I was like, I already told him I would, instead of just being like, oh, you should try that. Because he adds 4%
So that
to
would
your
be-
final grade.
Right, because it's not rated, so.
Computer program. I've never looked at 1.5.
I should have taken that class. Because this test was like, I was going to teach it because I was not good.
Not good.
Like, he's good, he's a good teacher, but like, then he does certain things that like, I've never heard of.
Apparently that's just something you can do. It's like, I didn't realize, apparently their tests are just completely different.
Like, literally, the questions were like, nothing that we've ever done, ever. And like, ever at all. And they were really like off the wall, like the one in clean space, your acceleration was like some weird vector equation. And then like, I think the one, I did not draw that.
Or is it 3 Tesla
So like I can either do the catapult competition or really want to do it. You need the same amount added to your final grade, like, but I don't know, like you can get 4% from paper. Like if you just bought the catapult thing, like you get none. So like it's expensive. A lot of paper. I'm stressed. I'm stressing. I'm not even. It doesn't even matter because they're not going to get my transcripts in time. I'm not going to get it by you.
I just went to like through the top thing. Did you know they had some perfect time? He's off the stage. That's like 30 minutes from here. And the other person was like from an hour away.
Dude, I have not been homesick at all since I got here.
Neither have I.
Living the dream.
So if that's your problem, then you have bigger problems.
Yeah.
And like, giving all the problems.
I tell my mom all the time, like, it's great here, you should move here. That's it, that's the extent of. Ever since I moved to Florida, I feel like I'm Florida. I hate it more than I did my anti-homesick. Yeah, we're going back.
Oh, I just presumed like that's the value doesn't.
All right, so since the bound is positive, x is positive, we don't need the absolute value from the derivative of the inverse secant. So that's going to help us simplify this a lot more easily. Okay, so our original integral is, what is it, u times v? Minus the integral of v du. So v du, you know, whatever. I saw people putting this in here like just like this, which is fine. At some point you want to simplify this though. So there's minus the integral of v du. Before you integrate this, simplify it. So that x and that x are gone. So this is a u substitution because this function's derivative is there as the numerator. So that's our du times a half. So we have this. Minus 1/2 our du, the integral. So that's our 1/2 from that integral. We still have this 2 here, so that's that 1/2 originally here. And then our remainder, I guess, or whatever, is 1/√u. So remember the radicals, or radicals in the numerator or denominator, those are always just powers of x, regardless of what the radical is. So that'll be u to the negative 1/2. So we've got minus 1/4 antiderivative u to the 1/2 divided by 1/2. So that's minus 1/2 Don't forget your first piece, though. Yeah? I think most of you did have that, so. And then the other question was, well, then how do we put these bounds in? Sorry, go back up. So then, how do we evaluate basically inverse secant at those things? So at 2, we have 2 squared over 2, 4 over 2 is 2. Secant inverse of 2. We have here minus 1/2, 2 squared, minus 1, 3. So we have the square root of 3 for that one. There's f of b minus f of a 2 over root 3. So 2 over root 3 squared gives us 4 over 3 over 2. That's 4 over 3 over 2. It's 2/3 inverse secant of 2 over root 3 minus 1/2. Again, we've got 4 over 3 minus 1. So minus 3 over 3, we've got the square root of 1 over 3. Or 1 over root 3. So there's f of a. So really, you just have to remember the relationship, because most calculators don't have an inverse secant button. They don't have an inverse cotangent button. They don't have an inverse cosecant button. So you have to remember the relationship between the secant and tangent, or sorry, secant and cosine, and then the sort of the identity for the inverse secant follows, or inverse cotangent or inverse cosecant. But so we'll just write it like this: the inverse secant of W is the inverse cosine of 1 over W. So the inverse secant of 2 is computed by saying, well, what's the inverse cosine of 1/2? And inverse secant of 2 over root 3 is, we're asking, what's the inverse cosine of root 3 over 2? So inverse cosine of 1/2 would be what? Pi over 3, because the cosine of pi over 3 is 1/2. So inverse secant of 2 is also pi over 3. We have this here, minus, we've got our 2/3. What's the inverse cosine of root 3 over 2? Or the cosine of what gives me root 3 over 2? Cosine of pi over 6 gives me root 3 over 2. So inverse cosine of root 3 over 2 is pi over 6. And then we have minus 1 over 2 root 3. So just combine our like terms, our pi's and our roots. We have pi over minus pi over 9. And we have minus our root 3 over 2 plus our 1 over 2 root 3. We have 6 pi minus 1 pi is 5 pi over 9. This is going to be, what, 3 over 2 root 3. So we've got 3, okay, minus 3 plus 1 is minus 2 over 2 root 3. And that's we have our exact answer, plus 1 over root 3. I think that's, let me just double check. So that's root 3, plus 2, 3. Yeah, I think that's it. Is that what your computer told you? All right. Yeah. So then, you know, with the other reciprocal functions, the inverses are computed the same way. They would just take 1 over their argument. So like if you had to compute like inverse cotangent of W, you would compute the inverse tangent of 1 over W. Do y'all have any questions on that? Yeah. This one?
Yeah. No, that's right, but you ran into that.
This one? Yeah. It's positive.
No. So, I mean.
Shouldn't
on
this
that-
be positive?
Yeah. So that would be just.
Yeah, so, but this was root 3 times root 3 over 2 times root 3 plus, that's a minus, 1 over 2 root 3. So this turns into a 3, so we just had a negative 3 plus 1, which was
Yeah.
negative 2. That's negative 2 over 2 root 3.
Yeah. So you put 2 negatives right there.
Oh, yeah, I see. Yeah, this negative is here. So this negative is just here, right?
Yeah.
Yeah.
And then so the answer would be.
Minus 1 over root 3, yep. Okay, thanks for catching that. Yeah. Yes, I agree. All right. Any other questions about this problem? I think that's the end for us then, for 8.2. So we'll take a break and then start 8.3. In 8.3, we're looking at trigonometric integrals, specifically like powers of sines and cosines and stuff. All right, then 8.3, looking at trig integrals, just some useful identities listed on the first page. The second page kind of gives us, we've talked about a few of these, but we're able to then look at the derivatives, or the antiderivatives rather, of all of the other trig functions. You know, really we've just looked at sine and cosine at this point. We did address, I believe we addressed tangent and cotangent in 8.1 with that logarithmic form. So we want to write tangent as sine over cosine. And then notice that this is a u substitution, either way you look at it. But the derivative of cosine is negative sine. So if we had this negative out here, we have this negative out here. And then that's in logarithmic form. So we talked about this one for sure. So the antiderivative of tangent is the natural log of the absolute value of secant. All of these you should know. You should just know them like you know the antiderivative of sine and the antiderivative of cosine. because they show up frequently in this section and in 8.4. Cotangent was a little bit more straightforward because that was cosine over sine. And that was already in log form. There's nothing we had to do. Or it's just a straight U substitution. Okay. Secant and cosecant involve multiplying by a form of 1. So I know we didn't talk about these yet, but we're going to take secant and multiply secant by a form of 1 as secant x plus tangent x. So maybe not obvious to utilize that, but I think once we see that, then we can say, well, if I looked at the bottom, what's the derivative of secant? Secant tangent plus the derivative of tangent. What's the derivative of tangent? Secant squared. So the derivative of the bottom would be secant times tangent plus secant squared. So notice what's on the numerator though. We have secant squared plus secant times tangent. Once we distribute. So since the bottom's derivative is on top, it's in logarithmic form. The antiderivative of secant is ln absolute value of secant plus tangent. And then we've got a very similar process with cosecant. So we write cosecant times the quantity cosecant x plus cotangent x over the same thing. See, especially for these last two, you don't have to remember what we multiply by to force it into logarithmic form. You just need to remember that the antiderivative of secant is ln secant plus tangent. All right, so this forces it almost in logarithmic form because we have cosecant squared plus cosecant cotangent on top, all over cosecant plus cotangent. What is the derivative of cosecant? Negative cosecant cotangent. And the derivative of cotangent? Negative cosecant squared. So you see our numerator is off the derivative of the denominator by a negative. So then that's when we do this. So Say, well, wouldn't it be nice if both of those were negative? If I'm going to make that negative, then I have to make multiply by another negative. So now that is in logarithmic form. Oops. So that's negative natural log of the absolute value of cosecant plus cotangent. Again, don't necessarily have to remember the process. Just remember that the antiderivative of cosecant is negative ln cosecant plus cotangent. All right. Do y'all have any questions on those?
Could you do it like you did the tangent x and pass the negative in and change the values?
On this last one? So past the first
No,
negative?
I mean, like at the end when you change it from negative natural.
Oh, right.
Cosecant x.
Yeah, since this is two terms, we don't do that. I mean, you could say that this is ln absolute value of 1 over cosecant plus cotangent to not have the negative there. But it's a little more cumbersome. Yeah. Yeah, so usually that negative is left there with that one. Yeah. Any other questions on those? Okay. So then we get into the process of looking at powers of sines and cosines, and we'll move on to powers of tangents and secants, and then briefly talk about powers of cotangents and cosecants. So here's our generic integral. We've got the antiderivative of sine to the m, cosine to the n, and these are our instructions. If m is odd, so if we've got an odd sine, an odd power that is, then we just split off one of the sines. We split off a sine x, and we put that with our dx, and that's going to give us, and you'll notice the similar pattern. The thing we split off, you want to put it next to your dx or your differential, because the thing you split off with your dx is basically like your dv. It gives you insight onto what your u substitution should be. All of these powers in 8.3 that we see of sines, cosines, secants, and tangents, cosecants and cotangents, they're all u substitutions except for even powers. But by and large, you want to think in this section, it's just an algebraic technique to get us into a u substitution. That's 95% of these. So the thing that we split off when sine is odd, we're going to put that with our dx, let u equal cosine, and then write the other remaining powers of sine using the Pythagorean identities. So let's see how this works. We're going to say that this is the antiderivative of sine squared, because we're going to split off one of the sines, and put it with our differential. So that's like our du. Everything we split off and put with a differential is like our du. So we're going to let u equal to cosine x, so that du, negative du, rather, is sine x dx. So our negative du takes care of the thing that we split off. And we just have to reconcile sine squared. Since our substitution was cosine, we need to rewrite sine squared in terms of cosine. And we do that with the Pythagorean identity. So sine squared is 1 minus cosine squared. And then we have our negative du for the thing we split off, sine x dx. Okay. So then since cosine is u, we have cosine squared is u squared. So minus integral 1 minus u squared du. So it's really the first type of thing that we encounter. If you see sine or cosine that's to an odd power, you just split one of them off. Regardless of if there's other sines or cosines to different powers in there, if we see a sine or a cosine to an odd power, that's the one we want to split off, and that triggers our u substitution. So we have negative antiderivative of 1 with respect to u minus the antiderivative of u squared with respect to u. You know, notice if we left this the negative 1 out, we would get some sort of constant of integration. I don't know, just maybe call that C2 for constant, some constant. But then the negative comes in here and multiplies that constant, which turns it into another constant. So, you know, however you want to handle your constants, I usually think it's just easier to put them in at the end. Okay, so distribute the negative that we had out front and then resubstitute. So that's the antiderivative of sine cubed. So with the exception of sines and cosines to even powers, everything else, even with tangents, cosecants, all of that, they're all u substitutions in disguise. It's just there's a particular thing we have to split off depending on the situation. Any questions on that? So here's cosine to an odd power. Notice the m and n's are still the same because the m is the power attached to sine, n is attached to cosine. Now it's saying that sine is to a real power, whatever, it doesn't matter. Sine to the negative 12th power times cosine to an odd power. You split off a cosine and then do the same process with how we approached the last problem. Okay. So whenever you see a cosine that's odd or a sine that's odd, that's the thing that you split off, which leads you to your substitution. We're going to split off a cosine. And the thing we split off, we're going to keep it with our differential, because that's essentially our du. So we're going to let u equal to sine x this time, so that du is cosine x dx. Our u substitution in terms of sine, we want this cosine squared then in terms of sine. So cosine squared is 1 minus sine squared. Okay. So it kind of like hinges on your u substitution, but our u substitution here is, we're kind of like reverse engineering it. Our u substitution hinges on what we split off. So we've got the antiderivative of 1 minus u squared du. So very similar to the last example, except we wouldn't have that negative. So u minus u cubed over 3 plus c. our u was sine. So it's just sine x minus sine cubed over 3 plus c. So really with a lot of these integration techniques, I don't know that you have to know any new information other than the process itself, because everything else will fall back on something we know. Are there any questions on example 6? Okay, then try example 7. Just take note here that sine is to the 4th, cosine is to the 5th, so we've got a cosine to the odd power. That's really all we need to focus on. It doesn't matter what the power on sine is, or cosine, as long as one of them is odd. If they're both odd, then you could choose either or method that we had in example 6, or the method we had in example 5.
Averages would be like, as long as it's not like 5 odd.
Yeah.
What's it called?
Expand. The only time that's not true is when we have the so it's like that's going to be more. Yes, exactly. That's going to be that's inverse. Oh, no, that's not. Right. That's sometimes what I choose. It's just
So, once I do that, I have.
Is this
Sine.
Did you notice on this?
I wish it was
Yeah.
To break the two separate.
Yeah, I think so.
So we can pick this.
Going minus
Because
2/7. Yeah. Yeah, that's good.
That's simple.
So then you have to expand it.
Yeah, so don't forget this is,
So
it's start square. Yeah, so this is, this would be 1 minus times 1 plus all that square. So you got 4 things to multiply there.
No doubt.
If you multiply sine squared, it's only truly cosine squared. Sine squared plus. So you can't
Yeah, once you write it,
Yeah, we're gonna cancel out.
1 minus x.
yeah.
After you flow it. Wait, because he said it's 1 plus
Oh, that's like, it's a plus than minus?
Oh, because it's sine of 4, you can literally decide how you did it. No, that was you did. Why did you tell us?
Into 2 cosine.
just expand 1 minus 1. Yeah. Squared. Yeah. Change it to 4. I would do this one
This would simplify if they're both minus, it would be like minus 2u squared. Would you give us the answer?
Take the next sine 9x over 9 minus sine over 7 plus 5 minus sine x over 5 right.
Sine 5x over 5 minus 2 sine the 7 times over 7 plus sine over 9
I can't wait till it's like cosine to the 19th and then we have to boil like u minus 1 up to the 7th power.
We get to what?
Right. When it's like instead of just 1 minus 2 at square,
Just use the binomial theorem,
yeah,
which is pretty easy. Oh, I learned it in pre-calc. It's like, it's what should, or you can use the Pascal's.
I can do that. But only works the first few.
But it's so weird. Oh, shit, I forgot to
1, 4, 6, 4.
I forgot that. Then triangles are blank.
11 is 1, 5, 10, 5, 1.
Now I have to go all common denominator.
1, 6, 15, 1, 15.
I feel like my math might be the.
5 and gone. 1, 2, 3, 4, 5, 6, 7. I there's gonna be an extra credit on this test. It's gonna be like sine to the 99, cosine to the 100.
2 times the product, and then the last.
Like, please solve it. I just have to put one more response.
That's what I got.
That's where I'm getting.
So, some people chose to like continue expanding. That's fine. At some point, you did end up use substitution. So it really doesn't matter at what point you use substitute. Just we can do that now after we change cosine to the fourth. We can write that as a difference of squares and then use substitute. It doesn't really matter. So we'll leave sine alone because that's our u. Cosine to the fourth, we want to think of that as cosine squared, and then this is just going to be our du. So then this cosine squared, we'll work on the cosine squared on the inside. That's our 1 minus sine squared. So you don't have that transference, I guess. It's not, sine squared. It is sine squared plus cosine squared equals 1, but it's not sine to the fourth plus cosine to the fourth equals 1. So that's u to the fourth for that one. This is 1 minus u squared for that one, and that's our du. Okay, so that was 1 minus sine squared here, but then that whole quantity is squared, so don't forget that. And to expand that properly. So you're really just looking at 1 minus u squared times 1 minus u squared. So it's not just the first thing squared and the last thing squared. So we expand that, and then we multiply by u to the fourth again. We're still just sticking with powers of u. Okay. Antiderivative of each term. And then resubstitute. Sine. All right. So most of y'all had the correct answer, I think. Either that or you messed up on the expansion here in this step. But I think after you corrected that, you should have been easily ended up with what we have. There was a question brought up, and it's I think important to realize. What's the difference between sine to the fifth x and sine of x quantity to the fifth? Remember, those things are identical to each other. The only caveat is when we have inverse sine. So this is why you see this notation anyways, is why you sometimes see inverse sine or inverse trig functions written as arc. So that's just the inverse sine. It is not the same thing as sine x to the negative 1. Sine x to the negative 1 is 1 over sine, which is cosecant. So whatever, insert your favorite trig function in there, and there it applies to all of those. All right. Does that make sense? Any questions on this protocol? Okay. So then we can talk about what happens if sine and cosine are to the even power. So like again, if we saw this as sine to the 4th times cosine to the 9th, then the process is we see, hey, cosine's odd. I'm going to split off one of those cosines. That's it. When they're even, we've got a different, a little more tedious approach, I think. So go back up to our identities. Remember these identities? And we had to integrate sine squared and cosine squared. So those are the identities that show up repeatedly multiple times when you have to integrate even powers of sine or cosine. So these are for even powers of sine and cosine. Those are the ones we default to. Power reduction identity, I guess, is what they're called. So, you can read the instructions if you want, but it's basically just repeated power reduction application. So we take sine to the 4th, and we write that as sine squared. And then we use the power reduction on sine squared. So we're going to rewrite sine squared as 1/2 times 1 minus cosine of 2x. So then we have to take the antiderivative of 1/2 times 1 minus cosine of 2x squared. So then, of course, before we actually do that, we do have to expand this. So I'll just do that over here. We've got our 1/4, and then we've got 1 minus 2 cosine 2x plus cosine squared of 2x. So then we expand that. Now split this up just so we can take note of where we're at. We have the antiderivative of 1/4 dx. We can do that one. We have the 1/4 times the negative 2, so we have minus 1/2 times the integral of cosine 2x. We can do that one. And then we have 1/4 times the integral of cosine squared of 2x dx. So that one needs a little work. The other two antiderivatives we can do. So then we're back now again to a sine or a cosine to an even power. We go back to those power reduction formulas and do it again. So how could we rewrite cosine squared of 2x?
1 plus cosine 4x.
Yeah. 1/2 1 plus cosine of 4x. Or that over 2. So then we're going to rewrite that cosine squared of 2x as that thing. So you can see we're going to get a lot of stuff to deal with. So, okay, yeah, we'll have our 1/4 here, we'll have this, and then we're rewriting that 1/2 times 1 plus cosine 2x.
Wait, isn't it sine?
No, it's cosine. They're both cosine. All right, is that okay? Where we're at, any questions? Let's just combine the constants here on this last one. There's 1/8. So split that second one. That last term rather. That last antiderivative. We'll split that up. Split it up whenever you want. It doesn't matter, but have these two. And these two antiderivatives here are kind of like terms, right? Because that's just a 1/4 and an 1/8. So you can combine those if you want. Eventually, you should combine them at some point. But anyhow, now we've broken that sine to the 4th down into 4 different antiderivatives, all of which we can compute. So the antiderivative of 1/4 with respect to x gives us 1/4 x minus 1/2. What's the antiderivative of cosine of 2x?
Sine of 2x over 2.
Sine of 2x over 2. Plus 1/8 x plus 1/8 times sine 4x over 4. And then whatever, we got a bunch of constants, we call them one constant at the end. We'll just kind of clean this up a little bit. So we have 1/4 plus an 1/8. What is that? 2/8 plus 1/8 is 3/8 x minus sine 2x over 4 plus sine 4x over 32. Let's see. That's a lot more tedious than the other ones we've done. You know, all of this stuff is tedious. This is why computers do everybody's work in the real world. Okay. So, you know, obviously with so much going on, the more stuff you have in there, the more likely it is to like forget a positive or a negative, or to reconcile those constants. You know, maybe you just have a 1/8 here, right? So just break these things up and don't try to get ahead of yourself. Just put things in their place and then take care of them after they're in their place, I think. Okay. Any questions on that one? All right, then. So how about cosine cubed of 7x sine to the negative 2 of 7x? What would we do for that one? No give up, huh? Yeah. Your brain is your computer in this class. So this sine of the negative 2 looks intimidating, right? But we do have a cosine to an odd power, right? So we should split off that cosine. Right? If we go back to this thing right here, let's see, n is odd. So if cosine is odd, sine is any real power, positive or negative, just split off the cosine. So it doesn't matter how scary the other power looks, as long as you have a sine or a cosine to a negative power, that's your process. You split that odd power off, one of them off rather, and then that's your U substitution basically. So once again, this is odd. We'll split this off, or one of them anyways, with the differential. So that's the antiderivative of cosine squared of 7x sine negative 2 7x. That cosine we split off, put it with the differential. So the ones we look at, they are very specific. You know, you could imagine, what if it was like cosine to the negative 3, sine to the negative 2? And so you can think of various combinations where it would be super difficult, maybe even impossible to find the antiderivative. But the ones we look at are very specific, that we can actually compute the antiderivatives.
So you take a cosine x, not cosine 7x though?
Yeah, cosine 7x, my bad. So we want to just keep that consistent, but yeah, that's the idea. Okay, just split one of those off. That again is our du, so our u is just going to be sine 7x. We'll finish that up next time. I'm going to hand back your exams.